Now, this is where things get a little bit more interesting. So everything that we've talked about, those four methods, they really work with tangent and secant as well. Okay. Um, the last one, we're not really going to cover power reducing formulas. That's not the last one. So really, it's the first two. Mostly the first two fit in here. Okay. And we're just going to extend them to tangents and secants. So you should be familiar with these integrals. Now, the first two you should definitely be familiar with. And the last two, even if you forget, you can use integration by parts to come up with these. I will never actually assume that you have these last two written down. They're shortcuts for the homework. I'd recommend you can have them in your notes, but I'll just assume that I don't remember them, so you're not going to remember them. You can use integration by parts to find them out if you ever need to. And I might sometimes say, hey, use integration by parts to do it yourself. But just as a review, the antiderivative of secant squared is tangent, because the derivative of tangent is secant squared. Same with the second one. The derivative of secant is secant tangent, so you can go the other way as well. Again, these ones will save some time, but you certainly don't have to have them memorized. The natural log of the absolute value of secant and the natural log of the absolute value of secant x plus tangent x. I'm gonna make some shrimp fried rice today. I'm really excited about it. You don't need to know that, but there you go. So we're gonna use these and combine them with our methods and do some examples. Integrate the following. Part A, integral of secant to the fifth x times tangent x. So now it's not as simple as going to that table and saying, oh, we have an odd secant and an odd tangent. What do we do? Because their derivatives are different. But it's the same idea. We want to do a u substitution. All right. In order to do a u substitution, we need either a secant squared by itself or a secant tangent by itself, because these are going to be our du's. So that's really what this video is about. Can we manipulate things to get these derivatives? So again, if we have a secant squared, we need everything else to be in terms of tangent. If we have this, everything else needs to be in terms of secant, which we can sometimes modify and sometimes get. Okay, so again, there's a couple of ways of approaching this. Let's try one. Let's say we don't know what to do, hypothetically. All right, then we can try it and say, well, we can get a secant tangent. We could also get a secant squared. Which one do we go for? I don't know. Let's try one and see what we get. And that's what I would encourage you to do as well. Sometimes if you don't know, recognize you have different options. Try one, see if it works, and then go from there. So if we write this as secant to the fourth of x times secant x tangent x, does this help us? Notice that this is the derivative of secant. Oh, we're almost done. This is the derivative of secant. This is our du. If u is secant, we don't have to use Pythagorean identity at all. Nice. Let u be secant of x. So du is secant tangent dx. So we have that right here. This is just our du. We have the integral of u to the fourth du. Oh, disappointed. Disappointingly easy. When are we going to get some harder stuff? When are we going to get some harder stuff? Pretty soon. All in good time. And we could check our answer. Yeah, because we get, using the chain rule, the constant would cancel. We get secant to the fourth x times its derivative of secant. Secant to the fourth times secant tangent is secant to the fifth tangent. Great. Now, if you want to, you could write some stuff in the table for this. I'm not going to. okay? Because I want you to be able to transition those methods, but you can. The book has some information on what to do with secants and tangents, and it's got a lot of good information, but I want to practice just applying that table for sines and cosines to secants and tangents. So part B, integral of tangent to the 6th x. I really haven't done a lot of these integrals, I'm going to be honest. So it might be a wild ride. So let's look at this one. We are either looking for a secant tangent or we're looking for a secant squared. Now, again, we have both. We have both options. So take a moment to look at what would happen in both frameworks and then choose which framework we want. I actually do definitely know which one is going to be nicer, this one, but I want to show this idea. So if we wrote this as, if we wrote this with a secant squared out, let's just write them side by side. If we said, okay, this is just tangent to the 6th of x times secant squared of x times secant squared of x. Again, we're always looking for a secant squared of x or a secant tangent to set up a u sub. Or we could write it as take out a tangent, take out a secant, and then write secant tangent at the end. So in this first one, the white one, this preps us for a u substitution where u is tangent. Well, that's not immensely useful, because if u is tangent, well, we still have a secant. But just like we can use the Pythagorean identity to turn sine squareds into cosine squareds and vice versa, there are Pythagorean identities for secants and tangents with squareds, right? There's these guys. Well, actually, you could do this whole thing with cotangent and cosecant. And in fact, I'm surprised the book doesn't do it with cotangent and cosecant, because everything with secant and tangent is almost identical to cosecant and cotangent. All right. But anyway, here's what we have. So all of this stuff would work with cosecant and cotangent. So yeah. This could be just a bunch of tangents and secant squared. Oh, u sub with tangent. That would work pretty nicely. This other one, if this is our du, we'd put things in terms of secant. And that's not going to work here. Because if u is secant, this is u cubed, but there's no way to get a tangent to an odd number into only secants. If this were tangent to the 4th as a result, that'd be the right answer. Which again means that if this were to the 5th, then we'd use the red method. All right, so just think about both and decide what's easier. So let's let u be tangent of x. So du is secant squared of x dx. So let's rewrite this first secant squared before we do the u substitution. Tangent to the 6th of x. Well, what is secant squared? Oh, we know that 1 plus, I don't know, it works when I click, but not with my pen. Secant squared is 1 plus tangent squared. And now the u substitution works perfectly, because this is our du, and all that we're left with is u to the 6th times 1 plus u squared. We can distribute and evaluate, and that's basically the end of this video. We get the integral of u to the 6th plus u to the 8th, which is going to be 1/7 u to the 7th plus 1/9 u to the 9th plus c, and u was tangent. Interestingly enough, we only have tangents in our answer. There are a lot of ways that this answer could be written. We could put some secants back in there. You just don't need to. There we go. The end. Let me know if you have any questions, and good luck. We'll do some more example problems of some maybe messier ones in the next video.